Okay, let's get into this. We've got some material here, excerpts from a document, diving deep into, well, what looks like a whole visual language,
Uh-huh.
welding symbols on engineering drawings. It sounds technical, maybe dry, but this is actually how designers communicate exactly how metal needs to be joined.
That's right. It really is a shorthand, sort of the secret code of fabrication.
So our mission here, looking at these sources, is basically to crack that code.
Exactly. We want to figure out why we even have these symbols. What are the essential bits you need to understand?
And, crucially, how to read them correctly. Because getting it wrong means the weld isn't what the designer intended.
Which can lead to big problems, costly ones often.
Absolutely. If you're working with engineering drawings, or even just reading them, understanding these symbols is, well, it's not optional, is it? It's about precision.
Spot on. Think of it like reading a map. Get the symbols wrong, you're lost.
Right. And here's something we need to flag right away, a real heads up based on the source material. While lots of the basic symbols look similar worldwide, there are two main systems, European and American.
Yes, the standards.
And they have fundamentally different rules for showing which side of the joint gets the weld based on the symbol's placement.
Ah, yes. That's a major point, a really critical difference.
Get that wrong, and well, you can imagine, we'll definitely circle back and focus on that key difference later on.
Good plan. So maybe we should start with the why. Why symbols at all? Why not just draw the weld?
Yeah, the source touches on that. The problem with trying to sketch out every single joint in detail,
Right, like that figure 9.1 example they give, showing a single U preparation.
it's crystal clear, that sketch. You see exactly how the edge needs to be shaped.
It is. For one joint. But picture a complex piece of equipment, maybe hundreds of welds.
Okay, yeah.
Trying to draw the prep and the weld details for every single one, it would take forever for the drafter.
And the drawing itself would become completely unusable, right? Just a mess of tiny sketches and notes everywhere. Total visual overload.
Precisely. Just clutter. So the solution, which they show in figure 9.2, is symbolic representation.
The elegant alternative, instead of a sketch, you get a symbol.
Exactly. And the advantages are pretty clear. It's simple, it's quick to add to the drawing.
It keeps the main drawing tidy.
Keeps it tidy, exactly. And you can pack all the essential weld info right there on the main assembly view without needing, dozens of extra detailed drawings.
Makes perfect sense. Streamlined communication. But are there downsides? Like, can a simple symbol really capture everything?
That's a fair point. There are limitations. These symbols work best for sort of standard joint types, the ones defined in standards like BSEN ISO 9692.
Okay.
They tell you that the type of weld, key dimensions, things like that. But they don't always spell out every tiny detail of the joint preparation.
So for really specific preps, you might still need an extra note or a reference?
You might, yeah. Maybe referencing a standard prep table or a separate detail drawing if it's non-standard.
And the big one, you can't just guess what they mean.
Definitely not.
You actually have to be trained to read them. You need to know the language.
Absolutely. Which brings us back to those standards we mentioned earlier. The source highlights the two main players.
The European one, BSEN ISO 2553.
That's the one. And the American standard, AWS A2.4.
Okay, so critical point. If you're looking at a drawing, you must know which standard it's using.
You absolutely must. Because, as the source stresses, while they might share some basic symbols, they have major differences in how they show information.
Differences that could lead to making the weld completely wrong if you misunderstand.
Yes, it's not just formatting. It's fundamental to locating the weld correctly.
Right. So for this deep dive, we're going to mostly stick with the European standard, BSEN ISO 2553, to kind of build up our understanding step by step.
Sounds good. And then we can highlight how the American AWS standard differs, especially on that key point about placement.
Perfect. Okay, let's dive into the nuts and bolts of BSEN ISO 2553 then. What are the absolute basic building blocks, the ABCs?
Right, so the source calls these the elementary symbols. And the clever thing is, they're often designed to look a bit like the actual cross-section of the weld they represent.
Oh, that helps. A bit of a visual clue baked in. Makes sense. The source lists a fair few examples. Square butt, single V-butt, single bevel butt.
Single V-butt with a broad root face, single bevel butt with broad root face, single U, single J.
And then some really common ones like fillet weld. That's the triangle one, right? You
Yeah.
see that everywhere.
Very common, yes. Also surfacing, for adding layers like cladding, and backing run, sometimes called a back weld or backing weld, plus the symbol for a backing bar, if one's used. These are your core shapes. Need a simple fillet, there's a triangle symbol. Need a V-groove, There's a V-shaped symbol. Pretty intuitive, mostly.
But things aren't always welded just from one side. What if the joint's symmetrical? Welded from both sides.
Good. For symmetrical joints welded from both sides, you basically just combine the elementary symbols. You stack them.
Ah, okay, so like a double V butt weld? Is that the one the source calls an X weld? Because it looks like two V's making an X.
Exactly that. And you also get things like a double bevel butt weld that often looks like a K, so sometimes it's called a K weld. Double U, double J, you just put the symbol for each side together.
Okay, got the type of joint covered. But what about the finish? The weld surface isn't always left as is. Sometimes it needs to be, say, ground flat, or maybe it needs a specific curve.
Right, and that's where supplementary symbols come in. About these, they're extra little marks added to the main symbol to show the required shape of the final weld surface.
Like if you need a weld ground flush, you'd add a flat line symbol for a flat single V butt weld.
Precisely. Or maybe you need a specific outward curve, a convex shape. For a convex double V weld, there's a symbol for that too, and one for a concave filler weld.
And you can combine these again, right? The source mentions examples like a flat flush single V butt weld that also has a flat flush backing run on the other side.
Yep, you build up the picture. Or a single V butt weld with that broad root face and a backing run.
You just add the symbols needed.
Exactly. And here's a useful detail from the source. If you don't see a supplementary symbol for the surface shape,
Yeah.
it generally means the exact final shape isn't critical. It doesn't need that specific control, so it can be left as welded within normal tolerances.
Okay, that's good to know too. So we've got the weld type, maybe combined for two sides, maybe with a specific surface finish. How does all this information actually get put onto the drawing? How does it tell the welder where the weld goes and how big it should be?
Right, this is the core structure. According to BS-EN ISO 2553, the main structure has two key parts, an arrow line and, importantly, a dual reference line.
Dual reference line. Okay, what does that mean?
It's really characteristic of this standard. It means there are actually two parallel lines used together. One is a continuous line, the other is a dashed line. You've got the arrow line itself, part 1, then the reference line, which is the continuous one, part 2A, then the identification line, which is the dashed one, part 2B, and finally the welding symbol itself, part 3, which sits on these lines.
Got it. Arrow, continuous line, dashed line, symbol. So what's the deal with the arrow line? How does it relate to the actual joint shown on the drawing? Arrow side and other side.
This is absolutely fundamental. The arrow side is just the side of the physical joint that the arrow on the drawing is pointing to and touching.
Simple enough.
And the other side is, well, the opposite side of that joint.
And the person doing the drawing just decides which end the arrow points to.
Pretty much, yes. They place the arrow. The main rules are the arrow has to actually touch one end of the line representing the joint on the drawing.
Okay.
And the other end of the arrow line connects to one end of the continuous reference line.
Now, here's something that seems really important, especially for welds that aren't symmetrical, like a single bevel butt weld. Arrow line has a very specific target.
Yes, this is critical. For non-symmetrical joints like a single bevel or single J, the arrow must point specifically towards the piece of metal, the joint member, that actually gets the edge preparation machined onto it.
Ah, so it's not just pointing at the joint, it's pointing at the specific part that needs the bevel cut before welding.
Exactly. It tells the fabricator immediately which piece needs that prep work. Huge detail.
Oh, okay, makes sense. Arrow side, other side. Arrow points to the prepped piece for non-symmetrical welds. Now, how do the weld symbols themselves use those two reference lines, the continuous and the dashed one, to show which weld goes where?
This is the absolute key convention of this dual line system. It's quite logical once you see it. Symbols for the weld details needed on the arrow side of the joint. They're always placed on the continuous line.
Always on the continuous line for the arrow side, okay.
And following that logic, symbols for the weld details needed on the other side of the joint.
They go on the dashed line.
Exactly. Continuous line, arrow side weld. Dashed line, other side weld. That's how the standard unambiguously separates the information for each side of the joint.
Clear distinction. But then the dashed line can be above OR, below the continuous line.
Yes, that's right. BS-EN ISO 2553 does allow that. There's both possibilities. The dashed line can float, basically.
Why allow that? Seems like it could be confusing.
The source actually explains it's an interim thing, a transitional measure. It was put in place to help people move from older national standards, like the old British standard, BS 499 Part 2, over to this European EN system.
Ah, a compatibility thing.
Sort of, yeah. It allows drawings to look a bit similar to the old style, while using the new logic of continuous dashed lines. It's like a bridge.
Okay. And what if the weld is perfectly symmetrical, like that double V or X weld we talked about, where the weld is identical on both sides?
Good point. In that case, you don't need to distinguish between arrow side and other side
Yeah.
because they're the same.
So you just don't use the dashed line.
Correct. For symmetrical welds, the dashed line is simply omitted. It shows there's several ways to represent a single V-butt weld with a backing run. All symmetrical, none needing the dashed line. It simplifies things when differentiation isn't necessary.
Right, makes sense. Less clutter if you don't need it. Okay, so we've got type, shape, location side. But what about size? How big should the weld be? Dimensions?
Yes, and EN 22553 has clear rules for this too. It's all about placement relative to the symbol itself. Dimensions that define the cross-section of the weld, like its depth or thickness.
Yeah.
They go on the left-hand side of the actual welding symbol.
Left side for cross-section. Okay.
Yeah.
And what about the length?
Length dimensions go on the right-hand side of the symbol.
Left for size, right for length. Got it.
Exactly. And there's an important default assumption in this standard. Unless you see a specific dimension, like an LE's value indicating penetration depth, all butt welds are assumed to be full penetration welds. Goes all the way through.
That's a critical default. Okay, let's look closer at those cross-section dimensions on the left side. So what are the letters used?
The main ones highlighted in the source are A, which stands for the throat thickness of a fillet weld.
Okay, A for throat.
Z for the leg length of a fillet weld.
E's for leg.
And A's for penetration depth.
And S is used for butt welds that are specifically not full penetration, right? Partial penetration.
Yes, or sometimes even for deep penetration fillet welds where that depth is a specific requirement.
And figure 9.8 shows examples like A6, meaning a 6mm fillet throat thickness.
Yep, or Z8 for an 8mm fillet leg length.
Okay, now shifting to the right side of the symbol. So this is for length dimensions, and it seems particularly relevant for intermittent welds, stitch welding.
Yeah. Exactly, where you have segments of weld with planned gaps in between. Here we use L for the length of one weld segment or element,
Hold the length.
often in parentheses for the distance between the centers or ends of adjacent weld segments. That's the gap, essentially. And N for the number of individual weld segments.
Then for number. Okay, so the example in figure 9.9, an intermittent double-sided fillet weld. It might show something like Z8 3x150 100.
Let's break that down. Z8 means 8mm leg length fillet. The 3x150 means there are 3 segments, each 150mm long. And the 100 means the pitch, or distance between the start of one weld and the start of the next, is 100mm. Wait, no, let me recheck the source convention. Sorry. E is the distance between adjacent elements, the gap. So 100 would mean a 100mm gap between the end of one 150mm weld and the start of the next.
Okay, 3 welds, each 150 long, with 100 gaps between them. And if it was double-sided and symmetrical, that information would just be on the continuous line, no dash line needed.
Correct. If it was non-symmetrical, you'd see potentially different dimensions on the continuous and dashed lines.
What if those intermittent welds need to be staggered, so the welds on one side are in the gaps on the other side?
Clever visual trick for that one. To show staggering, the weld symbols on the continuous line and a dashed line are drawn offset from each other along the length of the reference line.
So they don't line up vertically.
Exactly. That visual offset immediately signals that the intermittent welds are staggered.
Neat. Okay, type, shape, size, length, staggering. Seems pretty comprehensive. What about other stuff, things that aren't just geometry? Complementary indications.
Yeah, these are extra symbols for important process or location details. For instance, a little flag symbol sticking off the reference line, like in figure 9.01.
What does the flag mean?
That means it's a field weld or site weld. It has to be done out on site during assembly or installation, not back in the fabrication workshop.
Oh, that's a huge instruction for planning. And there's a circle symbol, too, around the junction of the arrow and reference line.
Yes, the circle means peripheral weld. It signifies that the weld needs to go all the way around the part or feature being indicated.
Like welding a pipe nozzle onto a tank wall all the way around.
Exactly like that, all around the periphery.
Can you even specify the exact welding process to be used, if it matters?
You can. If a specific process is mandatory, its standard numerical designation is placed in a fork added to the end of the reference line, opposite the arrow.
A fork, like a V shape at the end.
Yep. And the source gives common process numbers.
Yeah.
111 for MMA, or stick welding. 121 for submerged arc welding, SAW W. 131 for MIG welding, 135 for mag welding.
So you could literally see a symbol telling you to make, say, an 8mm fillet weld on site with the flag, all around with the circle, using the mag process with the 135 in the fork.
Precisely. All that information conveyed graphically.
Wow. The tail of the reference line after the fork, if there is one, that can hold even more info.
It can, yeah. Depends if the tail is drawn open or closed. An open tail just extending the line can include other standardized information in a specific sequence.
Like what?
Things like the required NDT acceptance level, maybe the welding position, like overhead, or even the specific type of filler metal consumable to use.
Okay. And a closed tail.
A closed tail, which usually looks like a box at the end of the line, is used to point to a specific separate instruction. Most commonly, it references a specific welding procedure specification, or WPS.
So you might see WPS 014 in the box.
Exactly. Telling the welder, go find and follow procedure number 014 for this weld.
Okay, that is an incredible amount of information tacked into this system. We've really dug into the European standard BSEN ISO 2.553. Now, you mentioned right at the start that crucial difference with the American standard, AWS A2.4. Let's revisit that, section 9.12.
Right. This is the big potential pitfall if you're not careful or if drawings get mixed up.
So what is the fundamental difference in how AWS A2.4 works?
The absolute key difference is how it indicates which side of the joint the weld symbol applies to. Unlike the ISO standard, with its dual continuous and dashed line, AWS A2.4 uses only one reference line, and it's always a solid continuous line. No dashed line is used for side identification.
Okay. So if there's only one line, how on earth do you know if the symbol means weld on the side the arrow is pointing to or weld on the other side?
This is the core logic switch. In AWS A2.4, symbols for weld details on the arrow side are placed underneath the single reference line.
Underneath for arrow side. Okay.
And symbols for weld details on the other side are placed on top of that single reference line.
Whoa. Hang on. So ISO uses which line the symbol is on. Continuous for arrow, dash for other.
Correct.
But AWS uses the position relative to the single line, under for arrow, above for other.
You've got it. It's essentially an inversion of the placement logic.
That's potentially disastrous if you mix them up. The same symbol, like a fillet triangle, could mean weld here in one system and weld over there in the other, just based on whether it's above or below the line or on a dashed versus continuous line.
Exactly right. With the same intended weld drawn using both ISO and AWS conventions side by side.
Yeah.
You can visually see how different the symbol structure looks to convey the same information.
Seeing them like that really drives home how important it is to know which standard you're looking at.
It really does. Checking the title block or notes for the applicable standards isn't just good practice. It's absolutely essential to avoid potentially serious fabrication errors.
So, wrapping this up, diving into these welding symbols, it's clear it's a really remarkably efficient language.
It truly is. It lets engineers communicate complex manufacturing instructions, joint prep, weld type, size, finish, location, process, inspection, all in a very compact, standardized graphical form.
It takes away ambiguity, well, assuming you know the standard.
Assuming you know the standard, yes.
And it creates that clear blueprint for the fabricator to follow precisely, minimizes guesswork, reduces errors. It's just a vital skill in that whole chain from design to finished product.
Couldn't agree more. It's the crucial link, really, between the design intent and the physical reality built in the workshop or on-site.
Well, that's been our deep dive into the fascinating and critical world of welding symbols, guided by your source material.
We've gone from why symbols exist through the basic shapes, adding dimensions and finishes, all the way to process details, and importantly, that stark difference between the European and American standards.
Which leads us to a final thought for you, the listener, to maybe chew on. We've seen that these two major standards, BSEN ISO 2.553 and AWS A2.4, while trying to achieve the same goal specifying welds, use fundamentally different graphic conventions, especially regarding placement relative to the reference line to indicate arrow side versus other side.
That key difference. Continuous dashed line versus above below the single line.
Exactly. So the question to ponder is, how absolutely critical is rigid adherence to one specific standard throughout a project or within a company? And what are the potential real-world nuts and bolts consequences if someone trained only in, say, the AWS standard encounters, misinterprets, and then fabricates based on a critical drawing that was actually drawn to the ISO standard or vice versa? What could actually happen on the shop floor or in the final product?